slight quiz. Who are they? Who know the guys with the brick wall in the back? Ah, this is the one on the left and on the one on the right. Sorry, your left and my right. So Jarek is the one with raised hands. Yes, that is correct. The other guy? Yep, it's Kuba. Wow, they're well known. This was a little bragging, and as of today, something next on the agenda would be fallacy correction, memory model, mostly Java one, short advice about what to do with the memory model and what about it, and lots of links for further reading. Honestly, I only have like 45 minutes if I want to get you on time to the next presentation, and this is really not enough to cover the topic. So, lots of links for further reading, and I hope you'll enjoy it. Hands up, who ever heard of this guy? Or no? One hand up. Mine is the other. Okay, 3 hands up. And what about this guy? Okay, somewhat more popular. And this guy? This guy is quite interesting. Totally. Pew pew. Not much? Ah, fine. Totally. Sarita Adve. Okay. Hans Ben. Alright, thank you guys for something more interesting. Martin Thompson. Cool. You guys are in totally right room. Totally so. So, who here doesn't program? Who doesn't write code? Hands up. Okay? Thank you for coming. If you would not program, I would actually encourage you to switch the presentation, because that's not for people who do not program. So, whoever heard about Moore's law? Okay? Number of hands. So you guys know G. Moore actually. You totally do. Gordon Moore, sorry. Andal's law. G. Andal is the guy who actually coined the term. He wrote a very nice paper about it. Who can explain concurrency versus parallelism? Okay, slightly less hands, but still some up. Who here codes with mechanical sympathy? Oh, now I'm relieved. If somebody would raise their hand, I would be ashamed because I couldn't. Who tries to? Who knows what mechanical sympathy actually means or is? Okay? Fallacy number 0. Java memory model is about garbage collection. It's about add-in, survivor, tenured spaces, memory management. Whoever has seen or read any source or actually witnessed somebody making that claim? Hands up. So, is it true? I see some heads shaking. Yes, it's not true. So, if it's not true, and it's not true at all, have you seen this picture? Yeah, so this picture is really, really horribly wrong. It's not about Java memory model. This is about Java memory management. If somebody talks to you about Java memory model and starts saying something like PMGen or tenured or add-in, they are talking about Java memory management, they are talking about GC, perhaps tuning, perhaps heap organization, but that's not what we're talking about today. There is a number of articles posted online some time ago by leading technologists, and they also were misled and actually got the things wrong. Some are still there. One of the topmost links on Stack Overflow about Java memory model is actually about Java memory management, so there is a number of confusion in the sources. Tread lightly. So this is actually the source of all data. Java language specification, section 17.4. This is actually the very formal specification of Java memory model. And what's interesting here is this part. Java memory model works by examining each read and then taking a look at write observed by that read and making sure that said write is actually valid according to certain rules. So what we can take from it? What read actually sees is what Java memory model is about, and whether the write is valid according to certain rules. What rules? Onwards. One of the best definitions of memory models at all, because memory models are actually quite broad topic, is one by Sarita Adve, an Indian girl who actually is quite onto memory models. She's like the most prolific author of papers relating to them. And she also wrote a very nice tutorial on how to create your own shared memory consistency model. So if you're in doubt, follow her. And she'll undoubtedly have some paper for you to read to clarify your inputs. So, the specification of how the memory system will appear to the programmer, eliminating the gap between the behavior expected by the programmer and the actual behavior supported by the system. Wow. What this actually says is that my expectation as a programmer can actually be quite wrong. There's apparently some gap of what the systems do and what they pretend they do. Okay, freaky. Onwards. Alexei Shipilev, our resident Oracle Java performance guru, says it even simpler. Basically, Java memory model answers one simple question. Wow, that's gotta be nice, right? What values can a particular read in a program return? So, guys, a question for you. Why would we actually expect that a read in a program would return something that we should actually even have a formal specification for? Clues, ideas? Why would you say that can happen? Why would we need actually something that would answer this question? Isn't this question like self-explanatory? I mean, I coded the program, right? So if I read the variable, it's either the default value of the variable or something that I actually change it to later, right? What I say, does it sound okay? Ah, you sense a trap, don't you? You keep silent. Okay, you're right. Everybody's allowed to keep silent. Whatever you say can be used against you. So, those two guys, Bill Pugh and Jeremy Manson, are behind JSR 133. And they are also behind one of the most often linked sites when it comes to Java memory model. They are behind the frequently asked questions site. And this site actually tells a number of interesting things when it comes to what is a memory model. First, they say that most cores have many cache layers. So that would be a simple memory for the core to actually go to. Simple memory that is very handy, very close, and the core actually can pull things out of it really, really fast. And what we actually have this multi-core system, and two cores try to look at the very same value. What will they get? So basically this depends on whether the memory model that we have is strong or weak. This depends on a number of things hardware related. And we'll talk about them more. But for now, take one line from this. Memory model defines when and who sees what. So, what is a memory model anyway? At the processor level, a memory model defines necessary and sufficient conditions for knowing that writes to memory by other processors are visible to the current processor, and vice versa. So basically, we're treading into multi-core systems. We're treading into something that's heavily related to multi-threaded programming. So, yeah, basically, another thread can alter something that I made. And with this, there is a question of what will I get when I read a variable? And that's what memory model is about. So it's about memory consistency. It's about being consistent. It's about what we see, we as the programmers, being what really is. It's something that is to help us to know what core and thread can see and how this actually can botch my program. It's also about assumptions. Because you see, the memory model specification is one thing for us programmers, but sometimes among people like us, there are people who are really into the craft, and they don't stop with just writing business software. They start writing JVMs. And if you write JVM, your own implementation, if you actually are one of the creators of, say, JRocket or Hotspot or Azure, then you're onto something else entirely when you read Java memory model specification. You want to know what kind of optimization your JVM is allowed to perform. Everybody here knows that JVM performs optimization, right? Okay, so out of curiosity, where? I'm creating a Java program. Where will my code be optimized? Shout out. No wrong answers.
Everywhere.
Everywhere. Explain.
JIT compiler.
JIT compiler.
And the JIT bytecode compiler can only switch.
Bytecode compiler. So everywhere. Yeah, pretty much it. Another fallacy. Well, I don't really need to worry about Java memory consistency model since really smart engineers actually crafted it. Well, after all, those are the guys who didn't just stop at business software, right? They went into freaking JVMs. They are like geniuses. So, half true. Yeah, I fully agreed. Everybody who actually got to work on JVM and actually stuck his butt on it, and they really persevered in this tough environment, they are like freaking genius to me. I wouldn't actually be able to do it. Shipilev apparently is like 26 years old. I fully admire the guy with his knowledge. It's like, wow, miracle. Totally. Apparently, however, there is no talisman of functionality when it comes to technology. You can't actually pull out a framework and say, this framework will actually deal with all my troubles, because it just freaking won't. This just never works this way. Frameworks are designed for a specific purpose, and they do this purpose well, but if your purpose ain't that very purpose, pretty much you need another tool. It might be very close to what your framework does, but it's still another tool. So, JVM ain't different. It will not do things magically. There is hard work behind it, and there are people behind it, and people screw up. Smart people screw up smartly, but they still screw up. Besides, memory models are damn hard. And yeah, people from Java, they pretty much botched it. Final point here. You might be not a Java person, you might be a Scala person, you might be a Clojure person, Jython person. And newsflash, Java memory model is like designed with Java in mind. And I mean it, because when it came out, there weren't really other languages on the JVM. This happened later. So, how they botched it? I mentioned JSR 133 before. Hands up who heard about it. Okay, not many. So, JSR 133 is basically a crusade by Bill Pugh, who actually noticed that pretty much every single promise that the Java memory model does simply doesn't hold up. When they say that final fields are final, they aren't. When they say that volatile makes you actually be able to read the field from memory, nah, not really. And when they say that double locking, and locking generally, works, in some cases. So Bill actually worked this up on his own, and he started pestering people. He started pestering pretty much everybody. He went to the people who actually wrote the specification. There is a number of email threads between him and Gilead Bracha, who was one of the main authors of the specification. And you know, everybody, after exchange of couple arguments with him, they were forced to say, yeah, you're right. So JSR 133 came to be, and in Java Tiger, which is like pretty much old news because it's 1995, I believe, they started actually to work on a new memory model. So ever since Java 5, we have like new memory model, and all those things are supposedly fixed up. So are they fixed up? After all, smart people did it. Some of them. Which ones? Cross-examination of the witness yielded positive results. Something is on. So basically, yeah, volatile is now more sure than it was. Final is more certain than it was. And double locking, at least those cases that they found, those were fixed. I wouldn't actually put my money on double locking in like every circumstance, but still. There is yet another update going on. Its code name is JNM9 or DEPS 188. And basically within it, they aim to actually fix the remaining issues that they found, because there are next ones. Some of you might say, this is pretty low-level stuff. Totally irrelevant to me. Yeah, I used to think so. Then I discovered that it actually depends. So, first of all, there is this thing that everybody in the news keeps calling the multi-core era, with capital E on the era. Apologies for the misspell here. But it actually depends on what you write and with what. As previously stated, if you're not on Java, you might have problems. You might have different problems than pretty much everybody else. Second of all, the Java language specification and the memory model part basically deals more with the low-level side. And this actually means that those of us who write simple business software, aka some forms, crude applications, they might not be beaten that much. But then again, even those simplest apps occasionally suffer through a spike in traffic. And with the spikes in traffic, a very important question comes to mind, and that is, how do I perform? Is my application performant? Is it fast? Is it fast enough? And from there on, you're on to multi-threaded, and you're on to Java memory consistency model. I have frameworks for that. Well, yeah. Moore's law. Couple of hands were raised in the air when I asked about Moore's law. Anybody willing to actually tell us what it is? Louder? No, not really that willing, right? Okay. Basically, Gordon Moore was a person who was pretty heavy on semiconductors. He was totally into it. He made a PhD on it. He worked with Shockley, the Nobel Prize winner. And Moore was actually one of the people who started Fairchild's Semiconductors, the company which later actually started the whole Palo Alto thing. When Fairchild Semiconductors actually opened their headquarters in Palo Alto, pretty much everybody says, this is so rural. Whoever would actually want to commute there? Now look at the place. So Moore actually got asked once by during a business interview, how does he predict semiconductor business and market going onwards? And he observed that actually every year, people from the business, they actually managed to cram twice as many semiconductors in the space that they used to cram it. So we're pretty much describing miniaturization. This means we can get more on the same board. This kind of was quite well for 30 or so years, but quite recently, this year, he said that, yeah, that's pretty much it. So we can't get more cores, or more powerful cores, to be precise, we can't get more powerful cores as fast as we used to. What this means? This means the CPUs slow down. We're not getting faster. Well, we are getting faster, but not as fast as we used to. Now, Amdahl's law, why this is quoted? Because that's not actually a law. That's just an observation, rather. So Amdahl's actually wrote something different. He said that speed out of a program using multiple processes in parallel computing is limited by the sequential fraction of the program. And this is something we can actually try to portray as an equation. And yeah, this is more of a law. Unfortunately, it's also limited. However, it allows us to reason that if we want to optimize something using, well, throwing more processors at it, we can do this to a degree, and it's not as straightforward as one would think. What is interesting is that in 1967, when he formed that law, he wasn't actually discussing in favor of multi-core processing. That's actually rather omitted, but take a look. In 1967, for over a decade, people already have been voicing that single-threaded processors and single-threaded programming is at its limits. In 1967. And that only by making parallel multi-computing machines, we can actually gain anything. Yeah, sure. The picture on the screen is actually a Tilera processor, and it has like 92 cores. Tilera claims that the next model will have hundreds of cores. And newest Intel processor, I believe, has like 18 cores. So yeah, we do definitely head into the multi-core era. So data distance varies, and this means that everybody needs to know the cache lines. What are the freaking cache lines? Why? What's about the data distance? What's this about? This is the data distance. Please take a look. On the very first column, you can see everything in like nanoseconds. So it takes half of a nanosecond to actually get information from level 1 cache. That's like brilliantly fast, blazing fast. Then, if we actually take a look at the optimization in the code and we happen to mispredict a branch, like not this set of instructions will be actually dealt with. It will be that set of instructions. Oh shit, I'll need to actually scratch what I pulled from the cache and pull this one. Such a miss is actually quite cheap. 5 nanoseconds. Wow. It's cheaper than reference to the level 2 cache, which takes 7 nanoseconds. For comparison, if I'm actually to take a look at some data, to send something, to actually retrieve something from main memory, how would you say it first? Who already spotted this? Sorry? 100. Yes. It's first column, sorry, first row, second column. The violet. So, if we actually take a look, we can see that we're wasting cycles. This doesn't matter if my application is a simple CRUD. If I'm actually just retrieving data from the database, I have like 100 users, they most likely won't care. However, if I'm actually dealing with something where I want each cycle that the CPU can have to matter, then yeah, this freaking cares. This freaking matters a lot. And how you go about it? So basically, when you code, your code can either land within your cache line or miss it. It can fill it entirely or like halfway or partially. What happens if it doesn't fill it entirely? Well, some other data is taken from memory to actually fit into cache line. What happens if my code actually goes over the cache line, if it's larger than the cache line? Well, I need 2 cache lines. If I need 2 cache lines, I can pretty much forget about atomicity. What is atomicity? Atomicity is when I can do something in one cycle. There are instructions which promise that they would be atomic. These are hardware instructions. We're going really low level now. And there are APIs in Java which use those instructions. Now, what it actually means, we started from actually language memory model. Programming language memory model, specification of what thread can see what in what core, which cache and whatever. And now we're talking hardware. And that is because memory model is dependent on the hardware. Because if your hardware has no instruction for atomic operation, then we pretty much can't use it. Now can we? And there are hardware platforms which don't have them. So if it matters, where it matters. And this is already explained by Damian here. This is the place where your code can actually be reordered, optimized, changed, erased. First of all, it can be done on the compiler level. When we are actually going from the high-level language to the bytecode, this is where first optimization happens. And yeah, this is, for example, where that code can be removed. Cool thing. If my code would not get executed anyway, I don't want it to be converted to the bytecode. Now, that's not all. Then we have just-in-time compilation, which also happens to be incredibly complex and totally fascinating topic. And there is a number of things which can happen here. For example, we can reorder instructions, we can inline functions, we can unroll loops, number of things, totally cool. And then we go on to the hardware. And this is yet again somewhere where things like optimizations on the code can happen. Because pretty much every hardware producer, every CPU producer, they also have memory models, hardware ones. So that means the Java memory model occasionally will collide with the hardware memory models. Now, JVM is pretty much the abstract, right? It is the universal machine which looks totally the same whether we are on the AMD or Intel or pretty much ARM, PowerPC, you name it. So what this actually means is that JVM guys are coding to the hardware so that we don't have to. If they are coding to the hardware, that means that in some cases they will have to insert more instructions, use a different set of instructions than the others. So on a number of cases, different barriers are being used. Memory barriers, which are the instructions that I mentioned earlier. The instructions that actually take care of the atomicity, that make sure that the order is what we believe it is, what we actually expect it to be. These are some factors for why hardware matters. Hardware matters because we can have many caches, and cache can differ in size and types. Hardware matters because different memory bus technologies are being used. Hardware matters because number of registers can differ. Cache protocols can differ, and I'll talk about cache protocols in just a moment. Finally, functional units per CPU may differ, and number of cores on CPU also may differ. What optimizations are we talking about? We talk about reordering the code. We can talk about removing what's unnecessary. One of the largest gains that we can have is to remove the synchronize. Mutex was 25 nanoseconds on that screenshot I showed you like a few slides back. 25 nanoseconds just dealt away, if we can remove the mutex. That is why log-free programming and wait-free programming is so cool and so sought after. We can replace instructions, we can shorten machine code, we can actually do something really cool like Christian stores. Christian stores are actually looking ahead and seeing, this variable will be later changed to this and that value. Why don't I skip it entirely and just store the value already? And this is why caches matter. Caches matter because some are only per core and some are being shared across cores. Level 1 cache, the one who's so blazing fast. Level 2 cache, which is like 7 nanoseconds. Then level 3 cache, which is like several nanoseconds. Level 3 cache, if our variable is stored in level 3 cache, pretty much every core will see it the same way. If our integer is 5, every core will see that it is 5. But if, for example, for some reason, some optimization caused it to land in the fastest of the caches, then if it's modified here, the other caches just won't have a clue. So, sooner or later, whoever actually thought up that caches are cool realized that cache, well, there are two hard things in computer science, right? Naming things and in cache invalidation. So it's important to actually know whether we have caches synchronized or not. How do we synchronize caches on the freaking CPU? With a protocol, of course. So there is a protocol called MESI from Message Exchange, and this protocol has 4 states and was the basis for all protocols that I've seen on CPUs used in that regard. So Intel has its variant of MESI, AMD has its variant of MESI, and all other protocols also are based on this protocol. So it's like the mother of all cache coherence protocols. And MESI uses barriers, or actually Java people use barriers to trigger MESI actions. I've been talking about those barriers without actually explaining what these are. I just said they are instructions. Well, they are instructions, and they are actually helping with the buffers. In the previous slide, we have load buffer, store buffer, and write combined buffer. These 3 buffers are actually being flushed when a barrier instruction is found. And this is how it works. So we are filling up the buffer with write instructions. Write instructions basically are instructions to the CPU, write to memory. And when they happen, memory gets changed. When the CPU gets to instruction write to a memory, it writes to a memory, and whatever was there changes its value. Now, this actually, when we have barriers in the instruction, that means flush the cache. And this is powerful because with this, you may actually ensure that the order of the instructions is as human would like it to be. We humans are not capable of holding as many information as a CPU is able to. We can't remember all that. We're not meant to. So, with barriers, we're actually forcing the updates, and we're making sure that everything is coherent. That CPU 1, 2 to n see and work on the same thing. That I don't get data races, like for example that this or that thread raced to whoever gets first to the variable and modifies it away. Now this is just crazy. So we're heading in the end of the presentation. So words of summary and gratitude. First of all, the best advice I've ever gotten to about Java memory model is the one by Doug Lee that I'm presenting to you on this very screen. The best way is to build up a small repertoire of constructions that you know the answers for, and then never think about the JMM rules again, unless you're forced to do so. Do you know who Doug Lee is? Who is it?
He wrote Java Concurrency in Practice.
Yes, he wrote Java Concurrency in Practice. He's the author of a number of APIs that deal with the concurrency. He's one of the people who are actually heading the JAPS 188 effort. So yeah, when the guy says that pretty much nobody can routinely follow the rules of JMM and do it correctly, I take his word for granted. So, the best advice about the JMM: figure what works. Have simple programs and take a look at their outputs. Notice when you have threads deadlocked, data erased, or whatever. Have like several of those programs and know what to expect when you run them. And then, when you don't run them, or when you run them and they actually yield different results, not what you would expect, you know you're in for a hell of a nightmare. Because something changed, or something doesn't work, or perhaps an instruction set is different on the hardware platform you're running on. Stuff like that. Gordon Moore, the guy who actually coined the Moore's law, the guy who actually started Fairchild Semiconductors, and the guy who started Intel. He's the guy without whom this presentation wouldn't have been made. Same for Gene Amdahl, the guy who actually worked with IBM, then started Amdahl, and a number of other companies, and wrote a very influential paper which tells you how actually far you can go when you optimize code by parallelism. Because there is a number of things you can achieve with parallelism, but there are times when working on the sequential section of the program yields better results. And his paper from 1967 quite nicely illustrates this. Leslie Lamport. Oh gee, the guy earned the title father of distributed system. His definition of the distributed system is one of the best I've ever came across. Basically what he says is a distributed system is a system where a failure of a computer you never knew existed renders your own computer totally unusable. So basically, if I'm working in a distributed system and somewhere there a computer breaks down, my own computer stops working, just like that. Totally cool definition, by the way. And pretty much if you use it on the recruitment talk, yeah, you got some points. So he's also the person who actually worked on distributed system clocks. He's the first guy to actually be so vocal about problems with measuring time on a distributed system. Because, say, if my laptop and his laptop are connected, and my laptop runs and says that this is now like 5 minutes to end the presentation, and his laptop is saying that it's like 2 minutes past the presentation, then yeah, we kind of got a problem on our hands, right? Do you guys know about Heisenbugs? Heisenbugs are really interesting bugs. They are the bugs which actually start behaving different the moment you observe them. Peculiar, right? You cannot have such a bug. I thought this way when I read the definition. I thought that somebody is playing for fun. But, you know, the other day, a tester comes to me and says that, you know, Tomek, I don't have anybody else but you to work on a problem, and the customer says it's urgent. So basically there's this scenario which doesn't work. When we want to update the form, it won't get updated. Okay, which form? How can I get there? Replication scenario. Cool. I'm delving into it and going through the motions, and yeah, the tester is right. The bug is there. I can't do nothing with the form. So I'm running tests. Tests do not pass. I'm debugging tests to see what actually breaks the entire thing down. And you know what? I got into debug, step, 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 everything works. I can do everything with the form. There is no bug. What the heck? Yeah, the debug was the reason. Because with the debug, when I went step by step, more time passed. And by the time I got to 11 seconds, everything worked. The problem was clocks were not synchronized. And the data that was supposed to be inputted was not allowed to, because its timestamp was just frigging wrong by 11 frigging seconds. Nifty Heisenberg, isn't it? So time matters. In distributed system, it matters even more. it's actually important to have clock synchronization protocol. It's actually quite nifty to know what problems you can get into. And this guy has a body of work who's unparalleled for that. He's the one who actually coined the term sequential consistency. He's the one who actually first began talking about how difficult it would be for a distributed system to really be sequential. And we people, we're wired for sequential. You can't mess with time. Now, come on. Time is sacred. For us, at least. For computers, not so much. This is the very hot guy who spits fire, and he's actually the person behind the JSR 133. He's behind making sure that final, volatile, synchronized double-check locking work. The fact that Java memory model was fixed is thanks to this guy. This is the Indian girl I was talking to you about. She's the author of the very nifty tutorial for shared consistency memory models. Sorry, memory consistency model. Martin Thompson. He's the guy who actually is the most vocal proponent of the mechanical sympathy term. And mechanical sympathy is about cache lines. Mechanical sympathy is actually about coding in a way that would support the hardware, not go against it. There is a number of things when you code and when you want to go multi-threaded that your hardware can assist you with. And there is a number of things that your hardware cannot. And if you try to go multi-threaded against your hardware, well, that's gonna be a bumpy ride, at best. So, if you heard about Aaron protocol, it's his work along with Richard Warburton and Todd Montgomery. Really nice protocol, I recommend reading on it. And finally, some personal thanks. If Jarek Pałka wouldn't have kicked me out for 4Developers like 2 years ago, I wouldn't be here today. So he's the one to blame, partially at least. And there are folks who said to make more about when I did the Java memory model short presentation. And it's thanks to them here that I am. Leslie Lamport, Bill Pugh, Sarita Adve, these are links for you to actually use for later reading. And finally, some really tough reading, but also worthwhile. And yeah, if you get through all those books, tutorial, one short summary, and really long blog post, then I believe you will know more about Java memory models than I do. During the course of reading some of those positions, I actually discovered that I know nothing. Then I discovered that, yeah, now I really get the Java memory model. Then I discovered, no, I still don't know nothing. And it went on and on and on. And unfortunately, I can't really say anymore on what state of knowledge I am. So if you spot me say anything or spotted me saying anything wrong, just tell me so. I won't be mad. If you want to read about laws and find out actually where they apply, why they don't, and all that, you can. And finally, those are 3 guys which I believe should be mentioned too, because you can catch at least Tomek here on 4Developers and you can ask him questions. He really digs low-level stuff and he can explain a number of things, and some things better than I can. So, totally recommend it. Konrad is an Akka hacker who actually deals with the stuff. He's the person who is most likely to answer, when did you last coded volatile in your Java code? And he will answer like yesterday, because that's what he does. And Bartosz Milewski is a guy who also, besides being one of the leading functional programming bloggers, he's also the guy who actually dealt with C++ memory model. Because while Java was actually the very first language who introduced the memory model into the language, C++, Python, and other languages have already realized that memory model is a must if you want to do concurrency, multi-threading, and all that. So pretty much every major language now has a memory model, and Bartosz Milewski worked with Hans Böhm on the C++ one. So, my last thank you is to you, because you persevered quite nicely on a rather tough topic. And thank you very much for coming. Thank you very much for answering my question, doing the show of hands when I asked, and pretty much listening. Thank you.